Alright, this is page 73, chapter 3, page 75, chapter 3, problem 82. The problem states, Babe Ruth hit a homer over the 12-meter high right field fence, 92 meters from home plate. Roughly what was the minimum speed of the ball when it left the bat? He's going to ignore air resistance, which we just realized on Friday is a big deal. Assume the ball was hit 1 meter above the ground and its path initially made a 40-degree angle with the ground. Okay, so I've kind of got that picture drawn. Babe Ruth has just whacked the ball. Notice I still drew him as a stick figure, even though he was sort of a hefty man. Ball goes flying, some initial angle of 40 degrees at some initial speed that we don't know, that's what we're supposed to find. Ball follows a parabolic trajectory. There's a 12-meter high fence. Travels 92 meters. Ball starts 1 meter above the ground. That's our picture. I boxed the answer up here at the top just so that when we get done, I don't have to look around and see if I can figure out, hey, did I just do that right? Assuming I did, hopefully, as long as we get our answer, 33 meters per second. So here we go. I'm going to start this problem the same way I do every problem. I'm going to make a variable list, listing what I know horizontally and vertically. Because I don't know this whole V0, what I'm going to do is write the horizontal and vertical velocities in terms of that and just leave V0 as kind of a variable in there. So, horizontally, my original x velocity is the whole V0 times the cosine of 40 degrees. Okay, so this V0 is the whole magnitude of the vector, V0x the horizontal component, which I have not drawn in, but I think we've done enough of these to see that. Okay, vertically, the original y velocity is the whole V0 times the sine of 40 degrees. Again, we don't know what that is, what that V0 is, but we're going to find it. Alright, horizontally, our entire time our velocity stays the same because we're ignoring any air resistance or anything that would slow down the ball. And there's nothing pushing or pulling it to speed it up either, so that's our velocity there the whole way. Okay, our acceleration horizontally is 0 meters per second squared. Our time in the air, we don't know. How far has it got to travel horizontally? Got to go 92 meters. We know that. Vertically, our v final y, we do not know what that is. It's not the same as the original velocity because our starting and ending heights are not the same. Our acceleration the whole time the thing's in the air is 9.8 meters per second squared. And our time, we don't know. And our delta y. Well, since we're looking for the minimum speed that we're going to hit this thing with, I'm going to refocus the camera. Since we're looking for the minimum speed that we got to hit this thing with, well, what we're going to do is assume that it's going to go 92 meters, and when it's gone 92 meters, it's gone 12 meters high. So our delta y, maybe I should write it as y original and y final. If I did that, I'd say y original was 1, y final is 12. Or I can just write it as change in y. Change in y is a net change of positive 11 meters. Okay. Alright. For some of the situations, or for some of the equations you might use, you might get two answers for time, both positive. That's because when you use equations with time there, especially something with t squared and you're going to take its square root, you're going to find out that time is at 11 meters here and here, like it's at 11 meters above its starting height. So it's at a height of 12 meters total in two places. Those are both legit. What you need is the time then seems to correspond more with 92 meters horizontally, not with whatever distance horizontally that would be. So when it's 12 meters above here, it's not going to be anywhere near 92 meters away from the bat. So that's how you're going to have to look at your data for your answers as you get them and say, oh, that would make sense. Oh, that one does not for this particular situation. All right. So I clearly don't know quite enough information in the horizontal direction. I'm still going to start there just because. So horizontally, I could say that delta x is equal to the average horizontal times time. The average horizontal speed is the same as the original, it's the same as the final, so I can just call that V0 cosine of 40 degrees times time. And looking at that, I know delta x. I know cosine of 40 degrees. I don't know V0, I don't know t. So I'm stuck there. Now let's try the vertical motion this time. Vertically, there's a multitude of things I can try. Okay. Since I know delta y, I know acceleration, one might think I could try to use v final y, except that I don't really know v original, and so that's not going to work so well. So instead, I'm going to go back to our table. I'm going to go back to delta y equals v original y times time plus 1/2 acceleration times time squared, and that's acceleration in the y direction. Okay. In that situation, or in that equation, I can write some of these variables in terms of other things. So I'm going to go ahead and expand this a little bit and say delta y is equal to, instead of v original y, I'm going to call that the whole v0 times the sine of 40 degrees times time. And then I guess I could do plus 1/2. Instead of ay, I'm going to plug in negative g, as our acceleration is negative 9.8. G is 9.8. Negative g tells us what direction it's in. Squared. Okay. And then looking at that, I see, well, I don't know t, I don't know v0, I'm kind of stuck. But I have one equation with v0 and t that I don't know. I have another equation with v0 and t that I don't know. Two equations, two unknowns, solve for one variable, plug it into the other. Okay. So I'm going to try what I tried the last time. I'm going to solve for v0 here and plug it in, solve for time, and then plug that back in. The reason is that this equation's got time in the numerator. It seems like it might be slightly less algebra to solve for time that way. We prefer, typically when I solve these, I solve one equation for time, plug it in, and then I get v0 directly. That works out just fine too. What you're going to end up with is a v0 in the denominator over here. For some people that freaks out. I'm kind of cool with it either way. Just do whatever works best for you. So for me today, I'm going to do solve for v0 here. Okay, so I get that v0 is delta x over cosine of 40 degrees times time. I'm going to take that result, I'm going to plug it in right there for v0. So delta y is equal to, instead of v0, I now have delta x over cosine of 40 degrees times t times another t, times the sine of 40 degrees times t. This whole mess will be your plus negative gt squared over 2. That's the 1/2 gt squared. Alright, looking at this, these two t's cancel, so instead of having a t and a t squared, I just have t squared in there. That makes life better. Delta x, cosine 40, sine 40, this is all just going to be a number. I know delta x is 92, cosine and sine I can calculate on my calculator, so I know all that stuff. G I know, the only thing I don't know is t squared. So I'm going to simplify this a little bit. I'm going to say that delta y is equal to delta x, and sine of 40 over cosine of 40 is tangent 40 degrees, minus gt squared over 2. Then I'm going to do some magical algebra. This will become delta y minus delta x times the tangent of 40 degrees. So I just moved the delta x tangent 40 degrees to the other side. Next logical step would be to multiply by 2, divide by negative g, and that's all going to give me g squared. So first I subtracted this over, then I multiplied both sides of the equation by 2, and I divided by negative g. Alright, I'm ready to plug in some numbers and take the square root. So I get 2 times delta y, which is positive 11 meters, minus delta x, which is 92 meters, times the tangent of 40 degrees. That's all over negative 9.80 meters per second squared. I'm betting that this part right here is going to come out to be less, or a negative number. That's good. I'm dividing by negative 9.8. So if I take the square root of that, I get t. So t is going to spit out. So I plug this in my calculator. Break up my calculator. looks like I've got answers from other problems. 2 times the quantity 11 minus 92 times the tangent of 40 degrees. Close on my parentheses. I want to divide that by negative 9.8. I want to take the square root of that. And I get time in the air is about 3.68 seconds, which seems on the reasonable end. I mean, if you think about how long a baseball seems to fly through the air before it leaves the baseball park, 3.5 seconds or so seems semi-legit. Okay. And then plugging that in over here, we should figure out what the original is. So that's 92 meters divided by cosine of 40 degrees times that time, 3.68 seconds. Okay. Take a look at what I get there. 92 divided by cosine of 40 degrees times 3.68. You notice that on my calculator there, I did put a parentheses at the beginning and the end, so I knew I was taking 92 and dividing it by the whole thing, not taking 92 dividing it by cosine of 40 degrees and then multiplying that result by 3.68. Okay, and I get 32.64 meters per second. And if I was a big fan of sig figs, which I should be, I see that my answer was actually 33 meters per second, so that seems to fit.